Hello everyone and welcome to my talk with the title Complex Valued Embedding of Generic Proximity Data. My name is Maximilian Münch and I'll present our research from a joint research project of the University of Applied Sciences Würzburg-Schweinfurt in Germany and the University of Groningen in the Netherlands. Before I start with the main content, for those who are not so familiar with the topic of proximity learning yet, I'll give a short introduction and motivation. Input data for machine learning becomes more and more heterogeneous and generic, and so we have more and more data that is not in vectorial form, like for example texts or graphs or sequential data. But many machine learning algorithms still have the prerequisite that the input data must be of fixed length and real valued data and some other. Some methods, like in deep learning, word-to-vec, time-to-vec, protein-to-vec, can handle this, but they require a large amount of input data. If you don't have tons of data, an alternative approach can be the use of a proximity function to get a relative representation of the input data instead of using the absolute input data. With this proximity function, you can compare each data point to each other input point and measure how close or how different they are to each other. So here I've shown some examples for those expert proximity functions. There are much more, but important, in general, domain-specific proximity measures often show substantially better results than standard measures like the Euclidean distance. The only problem? Domain-specific measures like this are often not metric and thus violate mathematical assumptions of many algorithms. Why should we care? Why is this important? Those metric violations cause, for example, negative eigenvalues in the proximity matrix. So many effective optimization strategies cannot find optimal solutions. They can find solutions, but there is no guarantee that these are the optimal solutions. The optimization problem is no longer convex, and because of this, many classical, reliable methods, for example, the support vector machine, that is very, very solid, fail due to this indefiniteness. So, in summary, non-metric representations are often more natural and appropriate and fit better the given task, but they cannot be used in the models due to their indefiniteness problems. So, how can we still learn with non-metric proximities? How can we use these non-metric proximities? In general, there are two different directions. At first, we leave the data unchanged and create insensitive models, like models in the grind space. And the second way is to change the data to make them metric. And then, after the data is metric, we can use established, well-known models, like the support vector machine, for example. This is what we have done in our approach. We embedded data into a metric vector space. This is of course not a new idea and has been discussed quite often. Embedding of a symmetric dissimilarity matrix is always possible if the diagonal is 0, by using here double centering to get a similarity matrix S from the dissimilarity matrix D. Then we have to apply an eigendecomposition to get the eigenvalues and the eigenvectors, and then we take this embedding step to embed the data, the eigenvalues and the eigenvectors to a vector space V. The only problem, if Q is here not 0, so loosely said, if there are negative eigenvalues, the information that is present in the negative eigenspectrum is lost or transformed, because we use here an abs function to change the negative eigenvalues. Our reasoned idea is to preserve the negative contributions in the eigenspectrum by removing the abs function, and in the embedding step, all eigenvalues are used as they are without any modification. Because we do this without modification, all the information is preserved, and we can simply generate the original matrix again. So no loss of information. But now, if Q is not 0, so we have negative eigenvalues, the embedding matrix V becomes complex valued, because we take the square root of negative values. As we see later, this is only a small limitation. At first, we want to make our approach more efficient. So we made some tests with the Nystrom approximation, important here. The Nystrom approximation is also valid for non-PSD proximities. If we apply the Nystrom approximation to the non-PSD data, we reduce the costs of an embedding to almost linear costs, depending on the number of landmarks from the Nystrom approximation. Here is the algorithm that we applied to embed the non-metric proximity data. At first, we approximate the original matrix P via Nystrom. The second step here, we use the eigendecomposition to get the eigenvectors and eigenvalues. After that, we construct the modified Nystrom projection matrix W. Of course, this is the line here where the complex values arise in this algorithm. We take the square root of possibly negative values. And at last, we combine the complex valued Nystrom projection matrix with the KNM matrix from the Nystrom step above to finally get the embedded matrix. After we preserve the contributions of all eigenvalues, there's only one issue left. The number of machine learning algorithms that can handle complex value data is limited. For testing our approach, we applied the complex valued generalized learning vector quantizer from former work of one of the authors. However, there are also further models to work with, for example, complex valued neural networks or complex valued support vector machines. I don't want to dive too deep into LVQ methods, so here's just an overview. LVQ classifiers are prototype-based methods. That means they are parameterized by a set of prototypes and a distance measure d. The classes are represented by prototypes, so each prototype is a representative for a certain area in the data space. New points are compared to the prototypes, and as an additional step, we applied relevance learning in the training phase in this context. What is the benefit and what is relevance learning? Basically, relevance learning is like a distance measure in which the weights can be learned on the features. Without going into more details, we also had to use the so-called Wirtinger calculus to update the differential operators from real-valued to complex-valued data. So with this in mind, let's have a look at our experiments. We tested 3 classification models, the LVQ method without relevance learning, the LVQ method with relevance learning, and as a baseline classifier, a nearest neighbor for complex-valued data. We tested these 3 models in tenfold cross-validation with the same landmark selection scheme shown here. These 3 classifiers were tested with these 7 data sets. Here we see they are of different sizes and different class constitutions, both binary class and multi-class classifications. Here are our final results from our test. We've shown the mean accuracy with standard deviation. We see the CGM LVQ, so the LVQ model with relevance learning performed very well during all experiments. Only sometimes the nearest neighbor was competitive, sometimes a bit better. The LVQ method without relevance learning was not as good as the one with relevance learning, but also sometimes much better than our baseline classifier nearest neighbor. In summary, and to come to an end, we proposed a complex valued embedding and processing pipeline to analyze non-metric or non-PSD proximity data. The approach shows promising performance on a variety of datasets and offers an efficient calculation of the embedding matrix with low costs and low errors. Further research includes the investigation of performance in different ways. At first, we made a comparison only to a baseline classifier. We also want to compare to other models like complex neural networks and complex valued support vector machines. And we also want to compare our approach to models that work in the grind space and thus leave the data unchanged. Finally, your take-home message from this talk. Here are 4 points. Don't be afraid of using non-PSD data representations. Approximation of non-PSD data with low error and low costs is possible. Embedding data is not restricted to PSD-only data. And last but not least, complex valued data is no limitation and sometimes even better than real numbers. So, thank you for your attention, and if you have any questions, please feel free to ask. or to write an email. Thank you very much.